Hi everyone and welcome to this episode of Keipert Labs. In today's video we're going to be discussing how we can redefine chemical potential energy and introduce a concept that we as chemists call delta H, which is what this is referring to. Okay, so for a start I want to talk to you about an example of a chemical reaction that we're more familiar with. So this is the combustion reaction for methane, which is this compound over here, CH4. We know that when we burn methane in the presence of oxygen gas, that we rearrange these atoms to produce two new substances, carbon dioxide and water, according to this equation. Now, one of the things that you've recently done, or looked at this idea that we can use by measuring the temperature change when this happens, that this allows us to infer the energy change that's involved during rearrangement. Okay, so this is one of the things that as chemists, it's hard for us to be able to quantify or to identify exactly how much energy is being involved in this during this process directly. You know, we can't watch the particles and then, you know, pick up a particle and look at it beforehand and afterwards and, you know, pick up atoms and do this. That we have to find more creative indirect ways of being able to actually work out how much energy is involved in this process. And one of the things that we do is that we have to look at the temperature change in the surroundings. Okay, so that what we can recognize, remembering that, so that we have a system, okay, and so energy can either leave the system to make the surroundings warmer, or it can go into the system, making the surroundings colder. Okay, either way, if we are careful in our observation of what happens to the surroundings, we can infer what is happening to the system. And as long as we conduct our experiment very carefully and we can account for the energy changes that are going on, then we can make quite a confident, draw confident conclusions about how much energy the system is releasing into the surroundings or absorbing from them. And by tracking the temperature change over here, that allows us to calculate this Q. Okay, and so that's, you know, what we can do by experiment. We can burn a sample, or we can heat up a sample, or we can mix things together, and we can keep track of the temperature change and then do our energy calculations using Q equals mc delta T. So we've done these calculations before looking at phase changes. But now what I'm going to show you is that we can actually go that step further, and we can carefully use them to keep track of energy changes in chemical reactions as well. And then look at how much energy is being transferred, and then that can help to quantify the bar charts that we've been using for a chemical reaction. Okay, so if I come back to this particular equation, okay, I'll get rid of that label there because we've identified that that's what this substance is. Okay, what we identify is that in this situation, that 890 kilojoules of energy is released to the surroundings for every 1 mole of methane. Okay, so I can write that as 890 kilojoules for every 1 mole. Okay, so for every mole of methane, that's how much energy will be released from the system into the surroundings. Okay, so there's a couple of ways that I can represent this. Okay, some are visual, some are quantitative, and some also then kind of taking to that next level. Okay, so the first thing that I can do is put the energy term into the equation. Okay, so let's treat our 890 kilojoules of energy as though it's a substance that's being involved in our reaction. So what we're saying is that it's 890 kilojoules being released, that is leaving the system as this process of change is happening. So I could write it over here. Okay, so as 1 molecule of methane and 2 molecules of oxygen combine together, they form 1 molecule of carbon dioxide, 2 of water, and 890 kilojoules of energy. Okay, so now it's quite easy to be able to consider it like a product, or, you know, like one of our products or reactants, and therefore to do stoichiometric calculations with it. excuse me while I just adjust my camera mode for a moment. Okay. The second thing that we can do is that we can construct a bar. We can represent this using bar charts. All right, so what I might do is I might clear this canvas a little bit to give me a bit of room to be able to work with here. All right, I'm just going to set up the diagram that we need. Okay, so I've set up my diagram here. Now, rather than writing ETH, pH, and so on, because my whiteboard marker is not quite fine enough, I've just done T, P, and C for thermal, phase, and chemical, before and after. Okay, now just yeah. All right, I'm going to use a blue marker to illustrate the number of bars that are going on. So what we've identified is that 890 kilojoules of energy is being lost from the system. Okay, so what we've got is we've got a certain amount of energy that's coming out over here. Okay, as a looking at the final kind of process. Okay, so what that means is that we must be starting with a high amount of chemical energy. If I'm to sketch this sort of diagram here, oh, no, I realize that's off the screen. I'll kind of pop it just here. Okay, so I'm starting with a high amount of chemical potential energy, and I'm finishing up with a low amount. Okay, because I'm giving off that amount. So then that means, I'm going to start off with, I'm going to choose 4 bars of chemical, and I'm going to drop that down to 1 bar of chemical at the other end. Okay, so let's say that my substance is at room temperature to start with, so I've got 6 bars altogether. Okay, and so then what's going to happen is that I'm rearranging these 3 bars so that they will be moving into our thermal account. Okay, so we're going to have 5 bars of thermal. I've had my 2, and then I've added 3 as they've adjusted from there. And then what we recognize is that then over time, as this cools down, I would come back to room temperature, I'd have 1 bar of chemical, and I would have lost, I can't really draw the O in here, I'd have lost that 3 bars as Q, which we now could actually write as 890 kilojoules. Okay, so that if I'm looking at this diagram over here, so that once the reaction has started, it's rolled down the hill, and then the difference there is that 890 kilojoules. Okay, all right, so the third way that I could represent this now is to then introduce what I call delta H. So in chemistry, H is something that corresponds to a concept we call enthalpy. Okay, or which is stored chemical energy. Okay, so it's the formal chemistry name for what we have called ECH. Okay, so other chemists who don't use the concept of energy accounts like we do would refer to this as H and say, okay, so it's this amount of energy that's stored. Okay, and so then what we do is then we're saying, all right, well, if we want to look at how much this is changed by in a chemical reaction, we start talking about delta H, or a change in H, which is enthalpy change. Okay, so the enthalpy change. Now, the idea is that we might be able to look at a particular reaction and say, oh, I've got 0.15 moles of this, and so therefore this much energy has been involved. But the idea is that we want to express this value in units of kilojoules for every 1 mole, or I could write it like this, kilojoules per mole, so that then I can, like with stoichiometry, that I can translate that across any particular situation and know that, okay, for every mole of this substance, what would the enthalpy change be? What would the delta H be? Okay, and so that then I can actually confidently do calculations, or I can look up this data that's reported somewhere else, and that's based on someone else's experiment, and then apply it to my own. Okay, and so there's a few, and so what we would do here, okay, so let me illustrate that to you, is that we would have a chemical equation here, and then we would write that delta H is equal to minus 890 kilojoules for every 1 mole. Okay, that is a kJ. It looks like a 4T. Let me see if I can. Let's rewrite that in the spirit of editing and precision. Kilojoules for every 1 mole. That's what I get for using markers that are not super fine. Okay, now the sign indicates the direction of energy transfer. From the perspective of the system. Okay. So this is important here. So if system loses energy, that is exothermic, equals a minus sign. Okay, if the system gains energy, I've just realized that I'm kind of running out of space here. So endothermic, okay, equals plus, positive. Okay, so that sign is really important. So the reason that I wrote a minus up here is recognizing that this system of these particles loses 890 kilojoules of energy for every mole of methane that reacts. Okay, and so now I can use that notation and I can see that, and then I can start to work with that. And so this is what chemists all over the world will be familiar with. And so the delta H and then the sign of that. Okay, now I'll also just to show you how this connects with the other types of energy diagrams that other chemists would be a bit more familiar with. This one that looks like this. Okay, where we've got our starting energy, our finishing energy, and then the path that it takes to get there. What we recognize is that this distance here corresponds to our change in enthalpy, our delta H. Okay, so from the difference from the starting stuff to the finishing stuff, which in this case would be 890 kilojoules. Okay, and so then likewise, if I have a chemical reaction that starts here and finishes here, okay, then my delta H is going to be positive. I've gone up from low to high. My system has gained a certain amount of energy, and I can measure that. And so the idea is that what we're saying here, I realize this video is going a little bit long, I'll try to wrap it up very quickly, is that the amount of energy transfer that we're measuring in our experiment, we are inferring that comes directly from the amount of energy change that happens to the system, that there's no other outside influences that are mucking up the amount of energy that we're measuring. Now, if we carry our experiment out carefully, that's a valid thing to say. So what we have done so far is we've had this equation, Q equals mc delta T, okay? So the raw amount of energy relating to this equation. What I'm telling you now is that in situations of chemical reactions, we are allowed, it is valid for us to substitute now delta H into this equation. And this is an equation that you'll need to be familiar with, that it will be a part of everything that you do from now on, saying that when we're dealing with chemical reactions, that delta H equals mc delta T. Okay, so that the amount of energy change that's going on is directly related to the change in the energy of the system. Okay, thanks very much for watching. Bye for now.